Hello, I am Joseph George, an independent researcher from India. This video presents ideas based on my research into cold fusion, also known as condensed matter nuclear reactions or CMNS. I welcome you to watch this video.
Since 1989, reports of strange reactions inside jars of palladium and heavy water have consistently appeared in experimental physics. We see excess heat, elemental transmutation, and distinct nuclear signatures that shouldn't be there. But mainstream physics dismisses these results for one highly specific reason: the Coulomb barrier. In the standard model of the atom, two positively charged nuclei repel each other ferociously. As they get closer, that electrostatic pushback scales to extreme levels. To force those nuclei past their mutual repulsion and actually touch, you have to slam them together at immense velocities, kinetic energies equivalent to millions of degrees. That extreme thermal velocity is exactly what defines hot fusion, the violent, chaotic collisions that power things like stars. This creates a direct contradiction. We have persistent, observable anomalies in low-energy lab setups, blocked by a theoretical rulebook that says those reactions are impossible. Cold fusion has remained an unsolved paradox for nearly 40 years, but that entire theoretical blockade rests on a single mathematical assumption. When physicists calculate the Coulomb barrier, they assume the space between a nucleus and its electrons is completely empty. Look at this standard potential well graph. Two nuclei are mapped moving through a bare vacuum. Because there is nothing between them, they face the full force of each other's charge and are repelled. But what happens to the math if we calculate that interaction differently? What if that intervening space isn't empty at all? Replacing that vacuum with a structured medium allows the Coulomb barrier to be calculated through material displacement. This reframing treats the interaction as a mechanical sequence. To see how this works, we need to trace the logic from the start, redefining atomic structure, examining confinement in a crystal lattice, tracking the exact instant of fusion, and mapping how that energy propagates. By isolating this one mathematical variable, the vacuum, we move the field out of the realm of unexplained anomalies and turn it into a testable physics proposition. We begin with a known physical mechanism, mass defect. In every standard nuclear reaction, a small amount of mass goes missing, converting into energy. This is a universal process. It happens during stellar fusion in our own sun, in supernova collapses, and in ordinary radioactive decay. Researcher Joseph George argues that this missing mass produces a real, space-filling substance. And because mass defect is universal, this substance must surround every nucleus in the universe. The proposed anatomy acts as a density gradient envelope, densest at the nuclear surface, thinning smoothly outward. When two deuterium nuclei approach, their outer envelopes meet. As this material compresses, the electrical barrier between them drops. They no longer have to cross a massive gap of bare repulsion. Instead, they only need to close the distance through their already thin envelopes, displacing the material until a nuclear scale interaction is possible. The Coulomb barrier hasn't disappeared. It has simply been recalculated through a physical medium instead of through nothing. This density gradient envelope provides the mathematical bridge needed for two nuclei to reach contact distance without requiring extreme thermal velocity. But a lowered barrier is useless if nuclei drift apart in space. To exploit that advantage, they have to be held in sustained proximity. This is where the host material comes in. By cramming deuterium atoms into a solid palladium crystal, you physically confine them. The required condition is highly specific: a deuterium to palladium loading ratio at or roughly above 0.875. At that high concentration, deuterium atoms are forced into interstitial sites, the tight spaces between palladium atoms, and they don't sit still. Lattice vibration keeps them agitated, repeatedly shoving neighboring atoms into sustained contact, achieving a coherence radius of 1 nanometer. You do not get this degree of forced, persistent proximity in a loose cloud of free gas or an unconfined plasma. The lattice turns a random kinetic chance into a dense population of nuclei continuously hovering right at the threshold of fusion. So what happens in the exact sub-picosecond moment a confined pair finally fuses? Where does the released energy go? Standard models dictate that mass defect converts instantly into heat, throwing off high-energy kinetic fragments and hard radiation. But in a filled atom model, that energy converts into the space-filling substance occupying the lattice, driving a rapid, mechanical, spherical shockwave. This is the sub-picosecond pressure pulse. Because the conversion happens inside a dense medium, it generates a symmetrical mechanical wave rather than randomized heat. This diagram maps the resulting wave. The local energy density at the reaction site spikes to roughly 10 to the 9th joules per cubic centimeter, traveling outward coherently through the host material. This concentration of energy occurs on a timescale far too fast for ordinary thermal diffusion to account for it. This specific mechanical pulse explains one of cold fusion's most persistent mysteries. The energy propagates as a physical wave, causing excess heat and lattice damage, without producing the deadly hard radiation you would see in a conventional vacuum reaction. That massive pressure pulse does not immediately dissipate. It spreads forcefully outward into the surrounding palladium matrix. As it moves, it passes straight through nearby interstitial sites, where neighboring, unreacted deuterium pairs are currently trapped. The wave momentarily squeezes the envelopes of neighboring pairs, supplying the final push across the lowered barrier. If pushed across before the wave decays, that second pair fuses too, sending out a new pulse that hits a third pair, continuing the sequence. To be clear, this is not the neutron multiplication chain reaction that governs nuclear fission. There are no neutrons required as coupling agents. The trigger is an acoustic pressure pulse moving through a shared medium. Whether this process multiplies into a cascade or thermalizes into heat depends on three precise variables: the coherence length of the pulse, the lattice's acoustic properties, and the local deuterium loading density. Mapping this mechanical propagation identifies the specific variables, loading, acoustics, and pulse coherence, that govern whether the reaction cascades into a self-reinforcing process. This filled atom hypothesis is not sudden speculation. It is a theoretical framework with nearly 2 decades of continuous presence in atomic and condensed matter physics conferences. The atomic structure model underlying this theory was first formally presented to the scientific community at the ISAC conference in 2015. That initial debut took place in Madrid, establishing the foundation for how these density gradient envelopes operate. From there, the framework evolved. The application of the sub-picosecond pressure pulse to cold fusion was accepted as an oral presentation for the 27th International Conference on Condensed Matter Nuclear Science. Niagara Falls detailed the mechanical energy channel to researchers in the field. The model continues to expand into standard nuclear physics, with applications to high burnup fission structures scheduled for NUMAT 2026. That upcoming presentation in Halifax demonstrates the framework's utility in modeling a radiated fuel structure. The persistent survival and steady geographic expansion of this model across international venues validates it as a serious scientific framework that demands rigorous physical testing. Because of this mechanical clarity, the line between a minor heat anomaly and a runaway cascade is no longer a mystery. It is a tunable target. A researcher could apply a resonant acoustic vibration, tuning the mechanical excitation of the loaded lattice to deliberately drive confined pairs toward that cascade threshold. The author provides explicit ways to prove this theory wrong. The falsification program includes an acoustic boundary test with CR39 track detectors, single-event phonon spectroscopy, and a post-mortem defect helium census. None of this requires discarding the conservation of energy or rewriting standard thermodynamic laws. Removing the assumption of empty space places these anomalies back into the context of conventional physics. The lattice acts as a specialized medium for mechanical nuclear interactions.
My work has recently reached an important milestone. My abstract on condensed matter nuclear reactions has been accepted for an oral presentation at the ICCF 27 conference. In addition, my research on nuclear fission and nuclear fusion has also been accepted for presentation at the NUMAT 2026 conference, Canada. I believe that one of the fundamental barriers to understanding cold fusion and other condensed matter nuclear reactions lies in our incomplete understanding of atomic structure and, more importantly, of the mechanisms through which nuclear energy is released. If we can develop a clearer understanding of these fundamental processes, we may gain new insights into how low energy nuclear reactions could occur.